when I move things around here a little bit. I made this a really depressing title. Dementia and Decline, Unintentional Changes in the Brain. That happens, no matter what. All right, what does happen as we get old? Just like our bodies, our parts begin to wear out, our functions change, right? The brain uses a lot of our energy, and once you reach your peak, it's just all downhill. No, I'm just joking. We do have these common things that happen. We have a loss of gray matter, which is the space dedicated specifically to neurons at the end, their functions. Within the neurons, we have, here we go, a shortening of the axons along cables, so to speak, through which the electrical signal is moving. And along with that, we have reduction in the myelin, which you might recall is that often represented as a white protective sheath around the axon that allows the signals to travel efficiently. So we have a reduction in that myelin. And then we have the neurons, just the number of neurons are dying as we go forward, and therefore the number of synapses are reversed. And this has some consequences. Well, first off, this is probably too small to see very much of. I can't see it very well, so I might not be able to refer to it very much. But there's changes to the gyri on the outside of the cortex. More deeper grooves come into play. Changes in the surface area that become so important. We have the ventricles that are enlarging. The ventricles are the spaces in the brain. They look like empty spaces when you look at images, but they're filled with cerebrospinal fluid. The ventricles get bigger, which means the region of the brain gets smaller. And we have fewer neurotransmitters or fewer receptors and changes to our neurotransmitters, and that leads to changes in how fast people can process information. You'll remember that last time, our fluid intelligence, processing and rapid problem-solving speed or rapid synthesis of ideas. Attention span is impacted, whether someone can ignore distractions, that sort of thing. And interestingly, there tends to be an increase in moral decision-making compared to younger people. And we have changes in memory. So let's take a little look at all these depressing things. So first off, let's just skip this for a moment, come back to it. Let's just start here with normal aging. So in normal aging without disease, cognition is still impacted. The central executive region, sort of like the prefrontal cortex type region linked to memory parts of the brain, is diminished. So we have declines in working memory that is able to hold certain information in your brain and work with it at the same time. Resource allocation and monitoring of cognitive strategies. So knowing what kind of strategies you should be using to solve a problem. People will start to have trouble doing two things at once. It's not based on sensory deficits, it's just based on this reduction in the central executive. And if an older person and a younger person could do the same task and produce the same result, but the older person would need to use more parts of the brain. So use up more resources. So they're running out. And memory changes, just normal, just healthy and normal memory changes. Explicit memory, like two things. Memory that we can speak, that we're conscious of. All right, that's explicit memory. And we talk about episodic memories, recalling things that happened in the past. As opposed to semantic memory, which is just facts, like facts and information, like, in what direction is Chinley, things like that. Right? And so the episodic memories, the event recall seems to be harder because they're trying to put together time and like people in place. There's more varied information going into it, so that those details can get foggy. The tip of the tongue effect, everyone has probably experienced this. Someone says, oh, that star who did da, 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 da. And you're like, oh, yeah, I know that guy. Oh, what's his name? Right? And then a minute later, after you move on to a new topic, it comes to you and you're, I know the name now. Well, that happens more when you get older. And then prospective, we talk about retrospective and prospective. Retrospective, memory for the past, but prospective, remembering things you have to do in the future. And it's not too bad for older people, as long as they don't have competing things going on. as long as they haven't like tapped out their cognitive resources. If they're busy with a lot of other things, like they're taking care of their grandkids and cooking a dinner and there's a lot going on, it's more likely they're going to forget something that has to be coming up for them. Some notes can be important. And this is all just normal. Attention and problem solving changes, attention declines along with the senses. It becomes harder to ignore distractions, to concentrate when there are a lot of competing information coming in. It's harder task shifting, moving from one task to another. And reaction time increases, meaning it takes you longer to react, like in a driving situation, to react to a car or something going on in the road ahead of you. It just takes longer. That's that fluid intelligence kind of function. And as you know, the fluid intelligence, rapid problem solving decreases, but you can still solve the same problems as a younger person. It just might take a little longer. Crystallized intelligence, it increases depending on the age. It's, it's stable for a long time. The decline isn't like that for crystallized intelligence. And that's like the little tidbits of knowledge that a person has and their ability to use those to make good decisions. And so then that leads to what we might call wisdom. Maybe Kristen's grandpa has it. Maybe some of your other older people do. The ability to use all those tidbits of knowledge, all of that knowledge in practical ways to recommend to you good courses of action, make good decisions for themselves. And unfortunately, you can't assume that someone is wise just because they're old. Age does not necessarily bring wisdom. And sometimes people who have certain things that they've honed can be wise at much younger ages. So that's normal stuff, right? And then we run into things like dementia. And so what do we mean by dementia? All that is like the natural decline in thinking, remembering, and making decisions, except when it comes to interfere with one's life, then we call it dementia. Alzheimer's is a type of dementia that we're pretty familiar with. And it's defined by certain things in the brain, tau tangles and amyloid plaques we'll look at in a moment. Right now it's treatable. You can take certain things to maybe slow its progress, but once the plaques and tangles are there, they're there, and you're not going to recover from that condition. And as you know, it is associated with significant declines. Early, the changes in the brain might lead to subtle decline in thinking, like someone who just is asking the same question over and over, or just doesn't seem to be as astute as they would. Then we might have general confusion coming up, maybe intermittently coming up and then declining and up and then declining. There might be better periods and worse periods, but we might see a little bit of not knowing where they are or what the plans are, or they might ask a lot, what are we doing right? What are we doing next? Even though you just told them things like that. At stage 4, this person would have trouble even doing basic fundamental care like bathing and dressing would need help with. And then finally, not even recognizing loved ones, inability to communicate. The person that you loved, I put this image on here because that is what happens. The person that you loved and you still love, you're going to care for them, but that person, that personality is gone. And all they are is sort of unfortunately tangled up in this messed up regions in their own brains. And so what does it look like? Well, first off, what we're looking at here is the axon in a healthy neuron. Okay. And what you can see are we have these tau proteins, and what they do is they help push transport nutrients through the cells. They're good. We need that tau protein. But then if you look down here, we see the same neuron that's diseased. And you can see that one aspect of the disease that's notable is that we have tangles in the tau protein. No longer is it helping nutrients come forward. And in fact, it's preventing nutrients from coming forward. And so we don't have, the cell can't live. The cell can't live if it doesn't have the way to transport the necessary proteins through itself. And so you can see how it's all, atrophying. It's much thinner because it's not getting the nutrition. And the other thing that happens is in the white area around the nerve cell, outside of the nerve cells in that supportive, what we call the white matter. And we have abnormal pieces of protein in that area around the nerve cells, and they're called amyloid plaques, and they're kind of sticky. And so they form kind of clumps, and they block communication between the cells, and neurotransmitters can't get through. So that's the kind of thing that's happening. And when we have the loss of all that gray matter, we eventually have, you can see how much larger the ventricles are in the second image, and then how much larger these white areas, the ventricles, are in this bottom image. Well, that's because so much of the gray matter of the brain is lost. And so it's shrunken. And that's why the ventricles are so much larger. And so this is what we see often when we look at Alzheimer's disease. And I won't even ask, because I bet you there's not a one of you in here who hasn't dealt with this. I bet you everyone has seen it. And so being a bit aware when this happens, first off, it can be very stressful. One of the most stressful periods of life, if it happens to be your spouse or if you're the primary caregiver, because that loved one isn't really there anymore. You know, their personality has changed. And in fact, they might even not be any version of themselves. Like someone who never cursed or swore, the kindest, gentlest person, might, you know, become pretty irritable, crass, you know, cursing, swearing, talking in ways that they never would have talked before. A big problem is people with Alzheimer's wander away and get lost. You know, they don't know where they are, and they can still walk, and so it ends up being really frightening. The person who's providing care has to be really vigilant. There's not a time to relax unless someone else is taking responsibility. Maybe they leave things on, turn on a stove burner and leave it on, right? Or other things like that, turn on the water and leave it running. They may not even remember the name of the care provider and may be kind of unkind to them. And then probably this person doesn't sleep well. And when they're not sleeping, when you're trying to sleep as the care provider, they might get up and wander around. And there's that worry again, right? And so if you do take on this role of care provider, which a lot of people do, you love that person, right? You have to make sure. A lot of times you can get supportive care, but you have to make sure that you give yourself breaks, because that loved person, they wouldn't want you to sacrifice your life for them in most cases. And so the only way to get a break usually is to have a network of people offering this care. And then I had an aunt who cared for her mother in their home. The mother moved in with them, and she had very serious Alzheimer's. And it came to a point for her that it was interfering with her marriage. Like her husband they'd been married decades, you know, and they're caring for this older woman now, but it was interfering with her marriage. And Nana, what we called when she was younger, we no longer recognized anybody. And they finally made a decision to put her in a care facility. Audie made the choice that she needed to care for her husband and her family, who were going to be continuing to live. And they put her nearby in a care facility. They couldn't do it anymore. So just a recommendation to be careful if you get into this position, and make sure you give yourself breaks. Anyone who has maybe had experience need to add anything before we go on? Just a tiny bit more Parkinson's. Parkinson's is another condition that normally if you see someone who's kind of trembling or shaking like this, yeah, that's always the first thing I tend to notice. So it is linked to problems with movement, control, balance, and coordination, but it's linked to the dopamine system. So what the dopamine does, we often think of dopamine as just being the pleasure chemical, but it's also the motivation chemical. Like we wouldn't do anything, again, if we didn't have dopamine. Dopamine is linked to movement and motivation. And so this is interfered with because of nerve death in the basal ganglia. A person with Parkinson's has this slow nerve death, and so they can't intentionally move their bodies or control their bodies as they used to, and there's gradual changes. And so I don't have too much to say about that. The typical treatment is L-Dopa, which is we supplement dopamine, and it can be pretty effective for a reasonable time. There are side effects and risks, you know, associated with it, as with everything, but maybe better than. And eventually, you know, a person can lose their ability to walk and move around and things like that. can eventually kill a person over time. So that's the bad news. Now, neuroplasticity and intentional changes in the brain. We're going to start here by talking about Jody, a child who had something called Rasmussen syndrome, which led to really severe seizures in one hemisphere, and they took out half her brain. And so let's watch this little video about her story.
We are beginning to harness the brain's incredible ability to invent itself, then reinvent itself throughout life. This girl is a testament to the amazing resilience of the human brain. Young Jody Miller leads an idyllic life as a 9-year-old girl. You would never guess that she has undergone some of the most drastic surgery imaginable.
Happy birthday.
Jody's first 3 years were textbook normal.
Happy birthday, dear Jody.
Then, about 6 weeks after her 3rd birthday, a storm of epileptic seizures took control of her brain.
She couldn't use her left arm hardly at all. She could barely use the left leg, seizing a good deal at the time, multiple types of seizures.
Ordinary life became impossible. Medicines did nothing, and the seizures threatened to turn fatal. Desperate, Jody's parents brought her to pediatric neurologist Eileen Vining.
We found her seizures were all coming from her right hemisphere. And we knew that there is virtually nothing else, nothing but Rasmussen syndrome that can produce that picture in a young child.
Rasmussen syndrome is a degenerative brain disorder that disrupts the electrical activity that makes our brains work. Tiny electrical explosions were flaring up in Jody's right hemisphere. As seizures became almost constant, she lost control of her left side. Only one radical treatment option remained.
We knew that she was never going to have her seizures controlled with medicine, and we knew that she and her family faced taking out that half of the brain.
Okay.
Dr. Vining recommended a daring surgery called a hemispherectomy. It would be performed by pediatric neurosurgeon Ben Carson.
The whole concept of taking out half of a person's brain would seem to most people impossible. Human beings are incredible creatures with a brain that is beyond belief in terms of its capabilities, to the point where we can take half of it out and still function in a normal way.
85% of our brain consists of the cerebral cortex, which is divided into 2 hemispheres, each with 4 main lobes. The cortex handles many of our higher functions. Areas on both sides control thinking, movement, and sensation. But the right side controls our left side and vice versa. Jody would lose almost all of her right hemisphere, and the cavity would fill with cerebrospinal fluid. The operation has to be performed with great precision to avoid damaging the parts of the brain that control Jody's life functions, like heartbeat and breathing. The surgery went flawlessly.
What we're looking at here is an image, an MRI, that was done on Jody after her surgery. And what it shows us is the fact that we removed her entire right hemisphere. And what we're able to see here is indeed her very normal left hemisphere and all the beautiful gyri of her cortex. And we can see right down the middle, the right hemisphere that was there is now replaced by fluid.
But how could Jody function normally with only one hemisphere? It's because of a miraculous ability of the brain called plasticity. Our brains can actually change shape, creating new connections between neurons or brain cells to replace lost or damaged ones. Jody's left brain started reconnecting almost immediately.
At least as good as this. And if I remember, he wore pink just like you. This young lady had half her brain removed, went home, I guess maybe 10 days later, and was already walking. She was ambulating. She was able to walk out of the hospital. And that's because her left hemisphere had such resilience, such plasticity. It was able to say, okay, something needs to move her left leg. Whoa. You gonna open it? Okay.
Jody continues to work on training her brain to overcome the slight paralysis in her left side.
But enough, now that's very good. You need to do that stretching stuff, honey. You know that, don't you? Are you doing enough of it? I think so. Atomic sentence.
The human brain is just an awesome thing because every time I look at it, I say to myself, this is the thing that makes this person unique. It still is just such a wonderful thing to find a young person whose life now can move on, who's no longer having seizures, who's developing in a normal fashion. I take the good with the bad, and I say, this is a bad thing, potentially, that we have to do for an extremely good cause.
Okay, so in order, she was still sending stimuli up into her brain from the side of the body she couldn't move, the left side of her body. And because there was input coming in, the remaining part of the brain could take over and create those functions again. When she grew up, she did have some problems, like it was hard for her to do math. It's hard for her working memory to hold those numbers in her mind. She just didn't have enough real estate up there, right? But that's the power of neuroplasticity. So look, now we know that's true. Okay, and the question I'm just going to lead through a couple slides here is talking about how it's plastic after childhood. If that same thing had happened to an adult, would they regain the same strength, or would they have the possibility of regaining that same capacity? And in general, the answer is no, not exactly the same capacity. Plasticity is much greater in childhood. But nevertheless, there's still a lot of neuroplasticity in adulthood that rests on our own decisions. We've talked about this before. 3 mechanisms it can happen by. First, we can have neurogenesis, which is the birth of new neurons. We used to think that could never happen. Now we know it can happen. And it happens in particular in the hippocampus. A taxi driver study was the first one I had the privilege of. The woman who discovered this, or who ran the tests to discover neurogenesis in the hippocampus, got a Nobel Prize. And I had the privilege of being at her talk at University of Arizona and having dinner with her. And she did a study that we'll talk about in a little bit. That's birth of new neurons. Very rare, but it can happen. What usually happens with neuroplasticity is we have, as you know, increased neural complexity. We have new dendrites with receptors to receive information, and then that leads to more neural connections going forward through either more neurotransmitter or more receptor fields. That's common rewiring. And the last way is increased myelination. We can get greater efficiency in our neural functioning if we have more myelin. So these are the things that are happening in the brain when we talk about neuroplastic change. So first off, neurogenesis, we used to think it never could happen. We first discovered it in animals. It was McGuire and colleagues who discovered it in people. And so he was using mice, and he randomly assigned mice, and the mice they use tend to be homogeneous in terms of their genetic makeup. And they either were in this enriched environment like this one, with toys and things to do, and wheels and things like that, or an impoverished environment, just an empty cage. What they found is that in the enriched environments, when they were given problem-solving tasks, these are often mazes and things like that, the mice in the enriched environment did better. They could solve problems more quickly. After they died, they weighed their cerebral cortex, and it was heavier. There was more mass in the cerebral cortex, which suggests the birth of new neurons. And they actually could count the neurons in the hippocampus, which is the region of the brain linked to memory consolidation. And there were actually more neurons in the hippocampus. So that was demonstrable proof of the possibility of neurogenesis. Remember, we talked about how new neurons aren't born. Remember, they're all formed in this first, halfway through gestation. So this was kind of cool, kind of exciting. What do you think it was due to in the enriched environment? Any thoughts? Was it due to the exercise, the social stimulation, the mental tasks, you know, just figuring out how to use these different toys? What do you think? What'd you say, Cubby? Okay, that's pretty powerful. So in this case, they actually linked it most closely though to exercise. Because think of what happens when you exercise. Your blood starts flowing much more rapidly. Like if you're ever feeling really tired, it's a good idea to go to bed. But I mean, if you are really tired and you don't think you should be tired at that time, try getting yourself some exercise and see what happens. Get that blood flowing quickly, all of a sudden your brain feels stimulated. That was just getting more blood flow, more nutrients up to the cells in the brain. Exercise. This teaches us something. Okay, you might be saying, okay, we know now that neurogenesis, the birth of new neurons, can happen in mice. What about people? Well, that's, oh shoot. Oh man, I had such a nice segue and I didn't take it. We don't need to do this actually. These are cool experiments, but let's jump forward to the question I just asked, which is human. I shouldn't say neuroplasticity. Let me change that word to neurogenesis. And the taxi driver study. It is a neurogenesis is a type of neuroplasticity, but this is what this was specifically looking at. So this is what they did. There used to be this sweet little 2-minute video, but it seems to be gone now. But they used these taxi drivers in London in the pre-GPS days. Maybe you don't know about those days, but London now, London was created at a time when, you know, horses and buggies and walking paths, right? Really random, arbitrary. It's a huge maze. And the taxi drivers had to pass a test because it was a privilege to be a taxi driver in London at this time. And it was just called the test. And like they had to learn every road and every business in that city. It was like a year-long course of study. And they had to be able to answer questions. You're driving down Smith Street and your passion asks you to recommend someplace to go eat. What are you going to say? Boom, boom, boom. You had to know everything. So it was really hard mental work. Okay. And so 2 years even sometimes. Okay. And so they discovered afterwards, they could actually do an fMRI and look at the hippocampus, probably just an MRI. And they discovered that the hippocampus was had changed its structure. And so this is the results from the actual study. To orient to the slide just a little bit, let's look at first LH and RH, left hemisphere, right hemisphere. What's represented specifically is the hippocampus associated with memory. The lightly shaded or bar is the taxi drivers, and the controls are the same people, meaning that they also had a pre and a post test for the size of their hippocampus or the neural density in their hippocampus, but they didn't have any of the training. And what happened? We could see that in 3 regions that we looked at, in the left hemisphere and the right hemisphere, we saw the growth of an increase in size in the area of the brain for the taxi drivers. And also different responses. So we have increased neurons that are specific to the taxi drivers, new neurons being born in the taxi drivers when at first it wasn't thought that that was possible. And it was from learning these maps in this big city that required so much memory. So there's like demonstrable proof that if you put your brain through a workout memorizing all this, it rewards you with the birth of new neurons. A couple of other examples in humans again, musicians and non-human musicians. Think about someone who's playing piano all the time or playing a musical instrument all the time. Let's use, in fact, in this example, let's use someone who's playing a violin. Can you picture what that looks like? The left hand holds and presses the strings, the right hand holds the bow. Would you expect the 2 regions of the brain on the left and right side to be different in a professional violin player who's always using their left hand to press the strings and their right hand in a more general way just to hold the bow? Do you think that the density of neurons in the left hand would be bigger? They're expecting a lot of it. Play your guitar. We should see that in if you're doing it a lot. You have to do this a lot. And I guess we're just sort of showing you the data from their slide. Another interesting study, this one, so this particular musician one wasn't proof because a person might say, well, maybe the people who had already big regions of cortical space devoted to their left hand, maybe they're the ones who chose to play the violin. Like there's that argument, it's just a correlation. And so these other researchers, Dragansky, wanted to do an experiment. And all they did was they were using college students. And all they did is randomly assign people who were taught to juggle in a 3-month period. And other people who weren't assigned to juggle, who were just assigned to live their normal lives. So they taught people to juggle, basically. Would you expect to see changes in the motor cortex associated with this kind of coordination? And the answer is yes, they did indeed see that. Did it stay forever? Was this group who learned to juggle forever have larger regions in the motor cortex? And that answer is no. There were still some changes present 3 months later, but if they stop juggling, you lose that. Your part of your brain starts to be used for something else. So these are just a couple of the many studies of evidencing neuroplasticity. And I'm not going to even go into this. So here's the conclusion of a big body of research. Competitive plasticity. So first off, the brain is efficient. If there's any real estate that's not being used, another function is going to take it over. So for example, if you were to lose your sight, we have a lot of the brain devoted to the visual cortex. Some other senses are going to take that space over, and you'll have enhanced senses. If you knew how to play the saxophone when you were young and you did it a lot, and you developed parts of your brain linked to playing the saxophone, and then you stopped, that part of the brain is going to get taken over. Anything that you're not using is going to be used for something else. The infant wiring is like the dedication of space. And so we do know that there are differences in like the space allocated in different human beings. So I read an interesting book that described baseball players as having more receptors in their on their retinas than a typical person. Like they just had more receptors, like their visual system was just built that way. And so we do have those differences. But anyone can take whatever they have and make it bigger by their own choices. And so the 3 principles that are true throughout the lifespan, including in old age, if you don't use it, you'll lose it. It'll be consumed by other neural connections. If you use it, it's stronger, including bad habits. I don't know if you consider your video game, or maybe you like to watch true crime stories or something, or like, something that isn't all that good for you. Well, that too, you're devoting your real estate to that. My son used to know everything about the Green Bay Packers, and I was like, Matt, why do you want to devote so much of your neural space to knowing every bit of trivia about the Green Bay Packers? But, all right, that's where it was. And then this one, I did not give you the evidence. I skipped through the slides, but if you use 2 pathways at the same time, they become 1 pathway in the brain. The evidence that I didn't go through was a primate who had 2 fingers taped together. And instead of, once he had them untaped, no longer had 2 separate, he couldn't move the fingers separately because the brain regions linked to those fingers is called focal dystonia. They had become 1 brain region, and he had to reteach his brain that they were separate digits. So cool, right? So I didn't put too much down here, but what you need to do, and what you need to tell your grandma and even your parents to do, is to keep engaging in activities that will enhance neuroplasticity. A really good one of the best, is learning a new language. It's like just engages so many parts of the brain as you learn to speak and read and write and learn different ways of, that's an excellent way to do it. but also puzzles and games like Sudoku. I always misspell it. I think I misspelled it here. It's DOKU. And crossword, like hard crossword puzzles. Doing the same game all the time isn't going to benefit you that much because you're going to get really good at it. As soon as you get good at something, you devote less neural space to it. It's potentiated. So you have to do new things. You have to challenge yourself. As long as you're doing that, though, you're going to have good progress. But along with that is this big thing about exercise. You've got to get the blood flowing up to the brain. And so the sooner you do it, the better you're going to be overall. We learned that from our 100-year-old. But that exercise is what's getting things moving. And your older person that you care a great deal about, take them for a walk. And touch them. That stimulates just even sensory activity. So keep things going. So I was going to show this video, but I'm not. It's not that good, actually. But I am going to talk about one more thing with respect to this neuroplasticity, and it relates to an experience I had. This isn't me, but maybe you've seen these hiking poles. Have you ever seen people with these things? If you're a hiker, a lot of people kind of use them, and I never had used them, and I'm a really avid hiker. But my brother and daughter and I went on a backpacking trip in Paria Canyon 15 years ago by now. And he had read somewhere that you should use these hiking sticks. And so we got hiking sticks and used them. And I noticed after like 2 days of using those hiking sticks, when I didn't have them, I had a very definite sensation that I might fall down. And I'm not a falling down kind of person. But in that short time frame, I had come to rely on those hiking sticks to keep me upright and balanced. And my own system in that short time frame, this was like a 5-day trip, short time frame, my system reallocated resources, took it away from my balance system. I didn't use those things anymore. They have a place, but using them all the time, it creates a deficiency. And this is Michael Mercenich, whose work I cited a little bit earlier, has done a lot of work on good aging. And this is just one example of what you might consider. So this is the bottom of a foot. And the darker areas are regions with more density, receptor density, like with sensitivity, more ability to sense the environment and help with balance and all those things. And so you can see the dense areas on the outside of the ball, outside of the foot, in all the toes, quite sensitive. Okay. Now, a lot of older people lose their balance easily, right? And what do the older people do when they're feeling like they're going to lose their balance? Like if you're walking, you can picture maybe someone walking along and they feel unsteady on their feet a little bit. What are they going to tend to do with their eyes, maybe? Look down. Maybe they're also going to balance themselves on something, right? Mercenich says this is the opposite of what we should do. Because every time, it's like me continuing to use those sticks. So every time you look down at your own feet, you're preventing the sensitive regions of your feet from giving feedback. You're preventing your feet from giving feedback to your brain. Now, we tend to do this all the time because we wear thick-soled shoes like that, where the feet are just kind of locked into only certain movements and there's no ability for the toes to do their job. Sometimes the toes are even crunched. So there really is a very limited that the bottom of the foot can sense. And so what he suggests is that when a person feels like they're about to fall, well, they should stop and they shouldn't fall. They should make sure they're safe. But they need to then place their attention on the bottom of their feet because that's the richness. I skipped through that slide too. But your attention on the bottom of your feet will enhance the neural pathways up to your brain, the afferent nerves that are going up to your brain, giving your brain feedback as to whether you're balanced. And so instead of using a crutch as soon as you sense a crutch being, in this case, your eyes looking down or holding onto the table, he suggests that people should be in a safe place with someone watching so they don't fall. But then they should be taking their shoes and socks off and walking on textured surfaces and placing their attention in the input from the bottoms of the feet, which are very sensitive. So it's interesting, isn't it? You have to act opposite of what your impulse is. at least in practice situations. That doesn't mean that you want someone who's feeling weak to be on their own, putting themselves in a position where they might fall. You don't want that. You don't want them to be unsafe, but they can train the brain. And this is just one example of how we can be conscious in our decisions about neuroplasticity. So that's what I have there. And we are going to continue a little bit more here as per our class period, because I want to talk about stress, but does this make sense? Okay. The last thing that we'll talk about here is the role of stress. And I wrote down, what can a person control? And so let's just get some terms first of all. I was thinking I'd go on the whiteboard, but that might take too long. Let's first think about what stress is, and we can think about a stressor first of all. So a stressor is just anything that activates your stress response system. So you can have acute stress, like the people who are in the wildfires. They're going through acute stress, or the floods in Spain, right? So we can have some of these events that happen, like an immediate emergency or a short-term situation that requires a rapid response. Dr. Robert Sapolsky is the big name in stress research, and he often uses this example. Our stress response system helps us to get out of the way when we're about to be attacked by a lion, right? A lion's charging at us. A good stress response system helps us in that situation. But also things that would happen in our world might be, losing one's home, or a breakup, or, a natural disaster, or fire, or, losing your job. These are the kinds of acute stressors. And in the wake of those stressors, you might have an elevated cortisol, an elevated stress response. If it goes on more than a month after that stressor is passed, then you might need to get some help with that. And we talk about these stressors can be physical things that happen, chemical things that happen. Maybe you're exposed to something, or there's something drug related that's happening, or interestingly, mental. And this piece right here is the piece that is unique to us humans. Your dog is probably not sitting around right now worrying about whether she's going to be able to fall asleep tonight, or like whether that dog she saw out on the trail is going to hunt her down. Like, your dog isn't giving herself any stress. She's dealing with stress that emerges for real. But we humans have the great gift of being able to create stress for ourselves. And so, for example, one of the ways they use an experimental paradigm is they'll tell somebody, if they want to create stress for an experimental condition to measure certain things, then they'll tell somebody that the reason they're here for the experiment is they just need to go into the next room. They're going to be making a speech before a few professors. 10 minutes to prepare. That's how they induce stress. But is this person in any real danger? No, the person's life isn't at risk. All the person is doing is imagining this, and their body is activating a stress response. So when we say a stress response, like a symptom of a stress response might be irritability, or, crying or something like that, right? But what we really mean is, we just mean the physical things that are happening in the body, the physiological mechanisms that activate in response to stress, linked to sympathetic nervous system. We'll look at these in a minute. Increased heart rate, your body stops digesting food, you might wet your pants, it depends on how severe the stress is, sweat, all things like that. So acute stress leads to these physiological conditions. Often it's generated by just our imagining something. Just imagining. Right now, I bet I could stress about right now by talking to you about, tell me about all the papers you have to write coming up for all your classes. And I bet if you even name just one, your heart rate will increase just a little bit. I bet you. And so what we live in today is a world where we hardly ever have lions chasing us. And even natural disasters and big life events like losing your home or losing your job are rare. What we have are a whole bunch of little stressors that cause us to feel constantly pressured or overwhelmed. So we talk about chronic stress when we think about human beings, and we're going to talk about it as it relates to aging. So just a little bit about this stress response. So what might it actually look like in this world when we're talking about chronic stress, a piling on of small things that are making you feel pressured? Well, first off, fight or flight is sympathetic nervous system. Fight, flight, or freeze, sometimes it's called, okay? And we'll look at what sympathetic nervous system is actually doing in a minute, but what we might actually see, I think I reversed my slides here. We might actually see if it's activated, this fight might play out in our lives today as irritability, as anger, as aggression, as moving toward, all because of the sympathetic nervous system being activated in that direction toward fight. Flight, also sympathetic nervous system. So it helps you run away from the zebra. I mean, the lion, either have to run away or you have to fight, right? Fight's making you aggressive and angry, moving toward. Maybe the flight looks like anxiety, fear, panic, avoiding the situation that you don't want to face, or worrying a lot, or just even perfectionism, like trying to gain control of your world. So freezing is another sympathetic nervous system response, but it also activates the vagal nerve. It's like you can't move at all. And the vagal nerve is like nerve that scatters all around the body. It can help you relax, but if it's if it's like too much, then you can't move, you dissociate, you might become depressed, kind of an inactive, heavy feeling. And then another thing that people sometimes do when they're under stress is, this is not exactly part of the fight, flight, or freeze, but it's like people pleasing, like trying to resolve the stress by getting back into the social network that you have, avoiding conflict, putting other needs first, saying yes to everyone so people like you, right? That's just another way. So what is this stress response about then? It's our body taking action on our behalf. So here's what happens. So there's been a stressor. The pituitary gland puts forward particular chemical, ACTH, abbreviated, which goes down to your adrenal glands, which are on the top of the pancreas, kidneys. Ooh, I'm embarrassed. Kidneys. And in response, the adrenal glands put forward an appropriate amount of glucocorticoids, one of which is cortisol. And they also produce adrenaline, which we also call norepinephrine. And these get into your bloodstream and they cause these kinds of things to happen. So first off, your liver, we have stored glucose in our liver. It's called glycogen, and it is released into our bloodstream. So to give us extra fuel for what we need. It's also done like if you're starving or something like that, you're also going to be reducing the liver. Our blood pressure goes up. We sweat more. So we lose liquid from our body. We perspire. We get rid of the weight of the extra water in our body. Our respiration increases, and so our heart rate increases, those two inextricably linked. Our pupils dilate, and we maybe only see in front of us, and we don't see anything around us. And our digestion slows down or stops, and maybe we eliminate any waste that we have in our body, which is good because you don't want to carry anything excess around if you're running away from a lion. Now look, when you see this, look at all the different parts of the body that are involved. The whole body is involved in this stress response. And that becomes a helpful thing to remember when we're going to look in a couple of slides, I think, at what happens when we chronically activate it. And in order to do that, let's just look at a couple of terms here. Homeostasis, first of all, is the tendency to seek and maintain a set point. And this is your body doing this. It's not like you consciously doing it, but your body wants certain things to be steady. It's the ideal level of something, like an ideal level of hormones or ideal level of glucose. We can liken it to, you remember Goldilocks and the Three Bears? It's this one's too cold, this one's too hot, this one's just right. Okay, so homeostasis is like just right, that one. Oh no, I phased in my slides the wrong way. Ignore that on the right there. Allostasis, this is just a couple of things that we think about it is, but one way is that many parts of the body are involved in producing an appropriate response. So, you know, we have hormones produced in the pancreas, like adrenaline, for example. And then we can have allostatic load because so many parts of the body is involved in doing it, that it's too much, like it wears those parts out. And metaphorically, we might think of chronic stress as being just like we're trying to get to here. We want the porridge to cool down, but we keep heating it up and heating it up and heating it up and heating it up again, right? So we might think about it loosely that way, as it's just constantly at that high level and never coming back down. So let's just jump through all of this stuff and go right to here. So let's orient to this a little bit. What this is showing is what happens when there's a stressor. So the set point for homeostasis, let's say this is the set point for all of those body functions that are involved in the stress response. And they all want to be right here. Let's imagine that's the ideal homeostatic set point. Does that make sense? This line right here is the ideal for all those functions? Okay. And so what happens is stressor happens and they go up, right? And then they come back down below there. And then things get back to normal again if the stressor is done. If there's nothing else going on. And that's a nice, healthy system. You run away from the lion, you get to a safe place, your breathing slows down, your parasympathetic kicks in, you can eat again, you can digest again, your heart rate slows down, things are back to normal, okay? But what happens if we keep having stress? Well, then we have another stimulus. Whole body reacts, whole body changes and makes your stress level, you know, your heart beats fast and everything. And then it drops down again. But look, this time it's not getting quite down to baseline because what happened too soon? Another stressor. Oh my gosh, I'm late. You know, and I have a stomach ache and I forgot to, right? Another stressor. Now it's up here. Now look how far it is up. And after a while, when you chronically stress your system, you have a new set point. Like you never get back down to what was ideal, because you're constantly activating your system. And so that's wear and tear on your whole body across many regions of the body. So your body's wearing out. But now how specifically does this relate to aging? And for this question, let's just take a moment and look at telomeres. So you know what these are by now. These are chromosomes that are connected here at the center here. They've replicated themselves and they're going to split about and become new separate cells, right? You're familiar with this from early in the semester. So these are chromosomes. Well, each chromosome is tapped with what's called a telomere, which is like a little cap. And that cap allows it to, it kind of protects all that DNA that's in there. It keeps it nice and coiled up. It doesn't serve any purpose like this. The genes on this chromosome have to produce certain proteins. The telomeres are just not doing anything to really contribute to the function, but they're protecting the chromosome itself. And so our cells all have these. And the telomeres that we have are linked to how long the cell can live. So you can see what happens in a young person, a nice kind of a big telomere, but every time the cell replicates, one little segment of telomere is gone. And what happens when we get to the last bit of telomere? What happens when we use the telomere? It replicates and there's no more of the telomere left. Well, only three things can happen. First off, the cell can just become dormant, senescence. It can just stop making copies of itself and it becomes dormant. The cell can die. Or without the telomere doing its job of managing the DNA in there, the cell can just start replicating itself uncontrollably and cancer can happen. And so this is another illustration. Here's the cell. As the cell is one cell, look at, here's all the telomere. It replicates, the telomere goes down, it replicates again, less telomere. As it replicates this many times, no telomere left at all. So do you think that it means anything to have nice big telomeres on your cells? Would that be helpful to a person's longevity? Absolutely, Colleen, absolutely it would. Yeah, long telomeres are really good because the more of this you have, like, look at this. If this was a lot bigger, right, then this person would be living longer. There's still some telomere here. Now we don't have cancer. We don't have death of the cell. We don't have senescence because the telomere is still there, right? So on this previous slide, it said it's linked to the biological clock. Like this clock, this sort of idea that our bodies have a limited durability for life. That was exciting. Back in there. All right, now here's the thing. Stress erodes telomeres, and it even begins early in life. So children, even prenatally, but children who have a lot of stress, they have shorter telomeres. It's the functionality of the telomere is reduced. Later stressors, emotional disorders. So we have a relationship between stress and the length of these telomeres. And rather than me talking about it, let me just remember how long this is. I'm going to show you this because this is about the last of what I have, 12 minutes. All right. I tend to end early, but we do have, remember, 3 50-minute periods. Technically, I have you this long. I think it's a pretty good video, and he does a nice visual illustration of this process.
I want to start by saying that ever since I was a kid, I was highly fascinated at aging, and I always felt that one of the greatest mysteries was how and why we age and what can we do about it. So to solve that mystery, I think will have a profound impact on our future health. But unfortunately, in the last 60 years since Watson and Crick, the maximum longevity of humans hasn't changed at all, and the expected lifespan of an American has maybe increased only 15% or so, and the current rate of increase is actually lower than it was back in the 50s. So this is a miserable reflection of our approach to age-related disease and another example of Moore's law in reverse, more money and less return. So why did this happen? I think it's because the medical profession and industry both have been focusing on treating diseases rather than getting to what's the underlying causes of those disease. It's like a handyman who's continually patching cracked walls rather than fixing the foundation. So we need to change our approach and address the root cause of age-related disease, which not surprisingly will reside within the mechanisms of aging. And this should lead, I believe, to significant increases in both health span and maximum longevity, not by better treatments for disease, but by maintaining health and preventing disease from occurring in the first place. So that's a radical thought, but there's solid science behind it. It turns out that our cells have a built-in clocking mechanism, a cell division clock that ultimately leads to a suicide switch. And we can see that clock at the ends of our chromosomes, the protective tip. So I have a low-tech model here of what's going on. And it may be the exception to the rule about complexity, because this was the subject of the Nobel Prize in 2009 about how telomeres play such a critical role in aging and age-related diseases. So let's pretend that this is one of my chromosomes. It has a centromere at the middle, which is important for segregating replicative chromosomes between cells, and telomeres at each end. If this was to scale according to the size of that telomere, this chromosome would be about 100 miles long. So these are actually very small components, but critically important. So we know that every time a cell divides, due to a process called the end replication problems, telomeres get a little bit shorter. So here we are, I'm losing some of my cell division capacity. And Alyssa Eppel will later tell you that stress causes telomeres to shrink or accelerated telomere loss. So this is for the stress of giving a TED Med talk. And in addition, we know that lifestyle changes, that lifestyle impacts telomere biology as well. So I missed my morning run. Here goes a few more. And this is for the hot dog I had on the weekend. So, of course, the same thing is happening at the other end of the chromosome. So now I have a chromosome with critically short telomeres at both ends. And what this does, why it matters, is that this type of a chromosome is inherently genetically unstable. It's going to recombine. There will be further breakages within the chromosome. And this leads to loss of the ability of the cells to divide. And ultimately, tissues start to fail, tissues and organs, and we end up getting disease and die. So what can we do to address this issue? What are we doing to leverage telomere biology in healthcare? Well, we first discovered that short telomeres may be the best single biomarker of health and disease risk. And it turns out, in fact, that telomere length alone is a better predictor than most of the conventional biomarkers and independent from it. I'm not saying that we would be looking at telomere length only as a diagnostic marker, but it will be used in combination with others. So monitoring telomere length may be a powerful tool for better health, encouraging individuals to adopt lifestyles that might slow the rate of telomere loss or potentially even activate telomerase, the enzyme that helps maintain telomeres, thus increasing telomere length and consequently lifespan. Now, in terms of therapeutics, we're not quite there yet, but the enzyme telomerase, if you upregulate it genetically, you can see in cells and animal models that the vicious decline driven by telomere loss can actually be reversed. So someday we hope to be able to do this with drugs, and there's already a dietary supplement on the market discovered by Ch09 and licensed to TA Sciences, and that gets us partway there. So in conclusion, I'd like to say that this field of science has led us to through a doorway into a world that was just speculation 20 years ago. We had no idea that telomeres played such a critical role in aging. And solving some of these mysteries of human aging has allowed us to take the first steps through that door and hopefully towards a longer and more productive life for all.
Great. Okay, thank you, Cal. In the next 5 minutes, I may change your view of aging. So we all know that age is the biggest predictor of early disease onset. But it's not chronological age, it's biological age. It's how much our tissue is worn out. And we just heard from Cal Harley how flexible biological age is. Someone could look 10 years younger or 10 years older than their chronological age. So what's all this variance in aging? How can we understand predictors of this rate of aging? It's somewhere in this huge world of gene-environment interactions, and we know that behavior looms large, probably more than 50% of the variance in early disease onset. I'm going to talk about a factor that is not usually mentioned at all, that's invisible, but so pervasive and high level, it shapes behavior and it shapes biology, and that is psychological stress. So let's define stress. If you will, think about the most stressful situation in your life recently, and think about how you felt in the midst of that, coping with it at its worst. How did your body feel? What's the stress response? We know it well, that reptilian brain. We feel maybe tense, our heart rate goes up, our thoughts may race, our blood pressure grows up. This is the fight or flight response. So that's stress, right? Okay, I'm done, that's stress. So now you know what stress is. No, actually, that's the old story of stress. So that's a small part of the picture. We now know that stress seeps into the cell and changes hundreds of important biological processes, including rate of aging. So I'm going to focus on telomere length, this integrative measure of how cells age, the clock or pacemaker on the cell's life. About 10 years ago, I was very fortunate to collaborate with Elizabeth Blackburn, who discovered the cell aging system, and start a journey of trying to understand the malleable factors that affect rate of cellular aging. So we wanted to look at people under extreme stress, so we looked at mothers of chronically ill children, And we compared their telomeres to mothers of low-stress children. And the findings were remarkable. Their telomeres were dramatically shorter. This finding has now been extended to many conditions of suffering: depression, anxiety, exposure to trauma. So it appears our cells are listening to our suffering. Now, what is suffering? It's just a complex topic, but it's interesting to think, what is chronic stress and how do we measure it? I have a mnemonic for you, which is chronic stress is in part R&R. Not the good kind of R&R that you're thinking of, not rest and relaxation, but seeing red and rumination. So what is seeing red? This is the mental filter some of us are so good at interpreting danger and exaggerating danger, and especially threats to our ego. These are the types of chronic stress, the types of thoughts that are linked to shorter telomeres that really get our stress system activated. And rumination is when we carry around stressful thoughts long after the event happened, far into the future. In fact, some of you might still be having a few intrusive thoughts of that stressful event I made you recall. And that's an example of how rumination is, how sticky those negative thoughts are, and how we carry them with us and keep the stress response alive. So we now know that stress exposure, stressful thoughts, these are the things that dwindle our telomeres. But I'm going to take you to the new question, which is, do our cells know when we're doing well? So stress is time traveling, worrying about the future, ruminating about the past. Well-being is in part being present in the moment. So meditation is an example of training the mind to be present. Our collaborators at UC Davis recently finished one of the grandest studies on meditation. They put people up on a mountain in Colorado for 3 months and trained them in meditation. They compared their cell aging to a waitlist group, and they found that they had slowed cell aging in the meditators. So we've been wanting to look at that in people who are not meditators. So we started measuring mind wandering and presence of mind. And I'm going to show you, Sally will demonstrate for us what our findings are. So Sally can respond in 2 ways. On a good day, she's noticing what's in front of her, noticing the flower, so to speak, and she's able to be present and engaged and focused on what she's doing. It's a pleasant feeling. On a bad day, Sally is everywhere but here. Sally's thoughts are thinking about urgent things, timelines, work, her to-do list, lunch. Her thoughts are mind wandering. So we found that the more mind wandering and the less present focus and engagement in the moment, the shorter people's telomeres were. So you can see mind wandering Sally has more dwindled telomeres, which does translate into more of an immune senescence, an aged immune system. So what do we do with all this knowledge? It appears our cells are listening in and eavesdropping on our thoughts, whether they're stressful thoughts or it's a state of mind of presence and focus. So some of you still might be thinking stress is just in the head and doesn't get into the body. Look at today, the front page of today's USA Today. 40% of people are more stressed since the recession, more stress at work. We have an epidemic of stress. You might think about stress as a potent drug, and many of us are on high doses for long periods, and we don't even know it. It's invisible. So how do we take this into account? The implications of this mind-to-cell relationship are so vast, and we need to take them into account. Not just superficially offering a yoga class at our healthcare center, but in our institutions, in our schools, in our workplace, in our social interactions. We need to take this relationship into account as if our cells and our lives depended on it, because at a very fundamental level, they do. Thank you.
What we have, recommendations then for you to have your own best older years. Eat healthy, eat less, and reduce that meat kind of, it takes more effort, more work for your body to digest that. Do intentional movement to keep your muscles strong, especially as they start to weaken. Work against it, not with it. Work against the decline, don't just allow it to take over. Work with flexibility to keep your bones and joints healthy, and then use whatever it is you want to keep. If you want to keep your balance, then be mindful and aware of balance. And if you want to